No. Descartes' rule of signs. Okay? So Descartes' rule of signs. So what we've got here, we're doing our synthetic division, right? Trying to figure out the zeros of our polynomial. But when we do the zeros of our polynomial, we try to find all these P over Qs. The more composite a number is, okay, meaning the more factors that it has, when I look at the potential for P over Q, if Q has a lot of factors and P has a lot of factors, then we talk about how the fundamental counting principle told me to multiply the number of factors of P times the number of factors of Q, and that tells you how many potential values you'd have to try through synthetic division. We're going to do one here in a little bit where the numbers aren't all that terrible, but the P over Q's, the potential of them is ridiculous, so you would not want to have to do them all by hand, okay? So what we found out, you guys know when, like, graphing calculators kind of came into existence? Do you even know, like, so these calculators are, like, great calculators. This is one Cole has, okay? Doesn't graph, okay? But if you were to ask somebody that maybe graduated high school in, like, 1976, okay? My mom graduated in 1976. She didn't have access to one of those calculators. She had, like, you go to the bank and the bank gives you a free calculator. That was, like, the most powerful calculator they had, okay? You guys understand, like, you guys know what a Game Boy is? Yeah. Okay? The space shuttle that landed on the moon had less technology in it than the Game Boy, okay? And then we landed on the moon in what year? I don't know. Okay, good. All right, so, like technology, the technology that you have and the exposure, the extensiveness of that technology is relatively new. So talking about this stuff, why talk about if we've got technology to do it? I agree with that statement, but I think it's also important to understand and have appreciation for the people that, one, developed this, okay? You know, Descartes, you know, he's in the 1700s, okay, so obviously had none of this stuff. And then even maybe some of your parents or uncles and aunts were probably being introduced to kind of the first elementary size graphing calculators, okay? So, you know, you ask somebody that graduated in the early 80s, okay, late 70s, and they were in college algebra, they had to do this stuff by hand. If you ever had a conversation with Miss Coles, I'd ask her stuff all the time because it just intrigued me. Like sine, cosine, tangent on your calculators, you guys have the luxury of being able to type in any number that you want to and find sine, cosine, tangent of that number, right? She had to memorize pages and pages and pages of charts to do a process. If I say sine of 45.6, you could type that in your calculator and it gives you it instantly, right? Okay. They, in the 70s, had to have these charts, okay, that they would say, okay, well, 45.6 isn't on that chart. 45 is on that chart. 46 is on that chart. Now we have to do a process called interpolation that allows us to kind of bring from 45 that we've got the exact value for and 46 that we've got the exact value for, and now we use interpolation to kind of narrow it down to what 45.6 is. So they had entire additional processes that they had to go through that your calculators do for you instantaneously, okay? And I think this type of stuff, going over this information, even though we've got tools that can get us the answer much quicker, is appropriate. It is beneficial for us to kind of understand, you know, what those people had to deal with, okay? Because you maybe a little bit more appreciation for your technology and your efficiency, because you complain, oh, it takes me an hour to get through my homework. Well, back then, like 5 hours, okay? So that's something to think about. So what Descartes' rule of signs for those people allowed was, if I've got a list of this long list of P over Qs, Descartes' rule of sign gave me a little bit of foresight into how many zeros we're going to have, okay? We could prove this. It's not really that difficult of a proof, but we did quite a extensive proof last week, so I got to take a break from that. But what Descartes' rule of signs basically says, if you look at the variation in sign that occurs in your P of X. Okay? So variation means change, right? Okay? So we're looking at P of X. And I'm just going to count how many times we go from a plus to a minus or a minus to a plus. Does that make sense? Minus to minus does not get counted, and plus to plus does not get counted from term to term. So if I start at 5, x to the 7th, that's positive, goes to negative. There's one change in sign, one variation. These two are negative to negative, right? So that doesn't get counted. So I went 5x to the 7th to negative 3x to the 5th. Now we're going to go from negative 3x to the 5th to negative x to the 4th. They don't get counted. But now I got negative x to the 4th to a positive 2x squared. Is that a change from a negative to a positive? So that's our second sign change. And then we go positive 2x squared to positive x. That's not a sign change. We go from positive x to negative 3. That's another sign change. Okay? What Descartes' rule of sign says. Okay? Right here, I'll give you the first part of it. It says the number of positive real zeros of P of x is equal to the number of sign changes or that less than, let me phrase that again. Positive zeros is the number of sign variations or less than that by an even whole number. Okay, and I think that phrase, less than that by an even whole number, is kind of cumbersome. Kind of talk about what it means, though. What's the first even number that I can subtract something from? What's your first even number? Counting. If I'm counting, what's the first even number? 2, right? Okay. So when I start with, this says that we have 3 sign changes. So this rule right here is saying that you could have 3 real zeros, 3 positive real zeros, or less than that by an even whole number. I'll subtract my first even whole number, and I would get 1, right? 3 minus 2 gives me 1. Okay? So Descartes' rule of sign is saying you could have potentially 3 or 1 positive real zeros. Why is that useful? Let's go through our synthetic division. Let's say we've done 3 or 4 or 5 synthetic division processes, and I have found that I currently have 2 zeros that work, and they both were positive. What does it tell me next? What does that tell me if I've got 2 zeros through my work? I'm halfway done, 2/3 of the way done, whatever, and I found I've got 2 positive zeros. What's it tell me? What's lurking out there in the rest of my P over Qs? How many positive zeros do I have left over? I have 1, right? That makes sense? I have this long list of P over Qs, and I have found 2 positive zeros. Descartes' rule of sign says, in your list of P over Q, there's 1 more positive zero that's going to work. Okay? Or, let's think about this. This is a 7th degree polynomial, right? 7th degree polynomial. So it's going to factor to 7 linear factors. Let's say I found 3 positive real zeros. I found 3 positive real zeros. Maybe it's the first 3 I checked. They worked. They all gave me zeros. What does this tell me? It tells me I'm done with my positive real zeros, right? It tells me the rest of my P over Qs that I have, I don't have to check any of the positive ones anymore because you've already found them all. Does that make sense? Okay? And that could cut out half your list. That could cut out 2/3 of your list. Okay? Of P over Qs that you would have to try. So that's a nice fact to have as we're working through these problems. Okay? Now that's only positive real zeros. Well, you might be asking, well, what about the negative real zeros? So this is how you do negative real zeros. Okay, and it's a little bit more tedious, but it's not terrible. We can do it. Basically what they do is they say, well, take P of x and reflect it over the x-axis. Kind of visualize what's happening, not the the y-axis. Take P of x, flip it over the y-axis. So basically what it does, it says, okay, if you got all these positive zeros over here on the P of x, flip it over the y-axis and see how many of those show up as zeros on the left-hand side of the y-axis. Okay? So evaluating P at negative x and then looking at the sign changes there can tell us how many negative zeros we could have. Okay? So first thing you have to do is obviously go, and you can do this all at once. I'm just going to be kind of deliberate with it. So something like that. Okay? And then evaluate all those. So this is where I was saying you could do this all at once. If you know I'm going to plug in negative x for the 7th, and there's a positive number out here, well, that total is going to be negative 5x to the 7th. This is negative x to the 5th, but you're going to multiply by a negative, so it's going to be positive 3x to the 5th. This is an even number, so it's positive, but now that makes it an odd number, so it's negative x to the 4th. That's going to be a positive 2x squared. This is going to be a negative x, and then a minus 3, right? Does that make sense? Now what we're going to do is we're going to check, okay? Would you agree that from this first one here to there, that's one sign change? Negative to a positive. Would you agree that positive to a negative, and that's another one? So positive to a negative. But we go negative to a positive. So the third one. You go positive to a negative. So there's a fourth one, and then you go negative to negative. So this is saying we have four potential negative zeros. So the number of negative zeros of P of x is either equal to the number of variations in sign for P of negative x, or is less than that by an even whole number. Okay, less than that by an even whole number. Well, that means, essentially when they say that phrase, less than that by an even whole number, you're going to start subtracting from your initial value 2, and then 4, and then 6, and then 8, and then 10, and then 12. You keep multiplying, subtracting out multiples of 2, essentially, right? Until you get down to 1 or 0. And the reason for that, we're doing something about counting zeros here, right? So it should be a finite amount. Can I have a negative amount of something? No, I can't have a negative amount of zeros in my hand, or maybe a negative amount of dollars in my hand or something like that. It's not possible. So what they're saying is, subtract this phrase right here, less than that by an even whole number, basically just says iteratively subtract 2 or repetitively subtract 2 until you get a result of 0 or 1 and you stop. So if I subtract 2 from 4, I get 2, right? Well, 2 is not 0 or 1, so I subtract 2 again. 0 is 0 or 1, so I stop. So it means I could have 4 negative real zeros or 2 negative real zeros or none. Okay? So here's the thing, and there's some, I think, logical things to talk about here. If these are my potentials for real zeros, what degree did I have originally in my polynomial? What was that? It was 5x to the 7th, right? If I have 3 positive real zeros, okay, and let's say this thing crosses the x-axis 7 times. We know that a 7th degree doesn't have to, and I think if we graph this, it only crosses once, I think. I could have 3 real zeros that are positive, 4 real zeros that are negative. 3 plus 4 gives me 7 factors, right? Okay. If I had 1 positive real zero and 4 negative real zeros, that would leave me 2 non-real zeros. Does that make sense? When I say non-real, it means they have imaginary values in them. They have I in them, okay? Which could happen, okay? And does happen quite a bit. I could have 3 and 0. So then I would have 4 complex solutions, okay? Imaginary solutions, okay? Or imaginary zeros. We call them complex zeros. And the idea is that in the 1 and 4 left me 2 complex zeros. 3 and 2 would leave me 2 complex zeros. 1 and 2 would leave me 4 complex zeros. 3 and 0 would leave me 4 complex zeros. 1 and 0 would leave me 6 complex zeros. Does that kind of make sense? And the idea, when I say how many complex zeros I had, it was always an even number. Because what we're going to find out is that complex zeros always come as conjugates, okay, because of the quadratic formula and how we use the quadratic formula to work with them, okay. It's always come in pairs. But this is a tool to help us kind of realize as we're working. Let's say I'm going through this work and I have found that I have 5 negative zeros that are working, 5 negative zeros that are working. Or sorry, I'm going to try 3 negative zeros that are working, 3 negative zeros that are working. It tells me then I've got one more sitting out there that I need to find, right? Because I can't have just 3 as a final number of negative zeros. Descartes' rule says you're going to have 4 or 2. You can't have the 3 in the middle. Does that make sense, everybody? Okay. The next theorem that we kind of use in conjunction with Descartes' rule of signs is what we call the upper and lower bounds theorems. Okay, this is a very common type of theorem that shows up in calculus. You start talking about boundaries. Okay, and a bound or a boundary is something that I cannot go beyond. Right? Does that make sense? Okay. So by definition, when we talk about what a bound is or a boundary, we usually talk about them in regards to our number lines. So we have lower bounds and upper bounds. And basically what it says is if C is representing your zeros, okay? So the number C is representing your zero, the place where you cross the x-axis, okay? So as we say that A is a lower bound and B is an upper bound, if your zeros, for all the zeros that are of your polynomial that are real, if they fall between A and B, okay, then that means A was a lower bound and B was an upper bound, okay? Basically what it's saying is that if I've got my graph, say, and I don't care what the graph looks like, something like that, okay? There's a value, there's a value. All my C's are between that A value and that B value, right? Does that make sense? So that A is what we call a lower bound. That B would be an upper bound. Does that make sense? Okay. Now, as we work, okay, we might actually find instead of that being A, because it could be equal to, we might actually do work that ends up being A. Well, are all my zeros, and maybe that becomes B. Okay. But are all my zeros, that one there, 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 that I'm calling C, do they all still fit between A and B? So I could still call A a lower bound and B an upper bound. Okay. Now, they might not be, so when we're doing this, we might not find the most minimal lower bound. We might not find the most minimal upper bound, but we'll be able to find lower and upper bounds. Okay. Why is that useful? Well, we might go through some work. We might go through some P over Q work, and I'll just give you an example here that has 108 P over Qs. And I think it's a fifth degree polynomial. So I might go through 103 P over Qs of synthetic division before I get to my first zero. And that would suck. That'd be a total waste of time. But if I'm using the lower and upper bounds, almost instantaneously I would find out that I could basically cut off maybe 2/3 or 4/5 of that list of P over Qs almost instantaneously. Okay? So it's very important. You're going to use the upper and lower bounds. I think this would be something that most people would probably pay attention to and utilize more often than Descartes' rule of signs. Okay. So what the upper and lower bound theorem says, two parts again. Okay. The first part says if we take our polynomial and we divide it by x minus a, meaning then that the zero we're looking for would be positive. Okay, so it's saying where b here is greater than 0. B is a positive. So the number you put in your box for synthetic division is a positive number. Okay? If you go through your division and you get to the bottom row, your quotient row, and it says there are no negative entries, okay, no negative entries, then that value of b is what we call an upper bound. If that turns out that way, then you don't need to try in synthetic division any P over Q value that is greater than that. Okay? So looking at a remainder row, no zeros, no negative numbers, okay? And it doesn't even have to be a 0. So that value that shows, that B, doesn't have to give me a remainder of 0. It gives me a remainder of whatever. As long as that remainder is non-negative, okay, we're good to go. Now it says no negative, so it could give me zeros. Does that make sense? In my remainder line, okay, or my quotient line. The second part says if you're trying to divide by a negative amount, okay, if you're trying to divide by a negative C value, okay, this one's a little bit more wordy. Through synthetic division, if the quotient row has entries that alternate non-positive and non-negative, then A is a lower bound of the polynomial, okay, or for the zeros of the polynomial. What does that mean? So divide by a negative, and you're going to look for a remaining row, a quotient row and remainder row that alternates non-positive and non-negative. Why do they say it that way? What does that mean? What's non-positive? What kind of numbers are non-positive? Would you guys agree that negatives are non-positive? So why call it non-positive? Why not just use the word negative? What number am I, if I say negative, what number am I missing? 0, okay? If I look at the word non-negative, well, those are just positives, right? If I use the word positive, then what number am I missing? 0, okay? What this is saying, the reason they put this, because we don't associate a sign with negative or 0. We either refer to as non-negative or non-positive, okay, in whatever respect that we need to. Basically what this is saying is if your quotient row alternates positive and negative, you are going to have a lower bound. But then you get to a situation, sometimes there might be in that remainder row, that quotient row, there might be a 0 in there. Well, what do I treat 0 as? Do I treat it as a positive number, or do I treat it as a negative number? And that's what this is. This is why they use the non-positive, non-negative phrasing. When they use that phrasing, basically it means when you see 0, let it be what you want it to be. If it needs to be positive so that it alternates, let it be positive. If it needs to be negative so that we alternate signs, let it be negative. Does that make sense? So you let 0, any zeros in your row, carry the sign that is going to allow the rest of the row to alternate back and forth between negative and positive. Okay? So here's an example. Now they're and kind of understand how like questions and examples in these notes and even in your homework a lot of times are engineered. Basically what they do is they know what the zeros are of this first. Okay, and they're going to say, okay, well, if I know what these zeros are, let's just see, let's put some integers in here and just validate that all our zeros do fall between -3 and 2. So what they do now, and it's up to you, but they make their synthetic division a little bit different than the way I do. I don't know how you guys were taught with Mrs. Coles, but I always like to have that. When I was in Algebra 2, it was this way, and that's just the way I learned how to do it. So I like to keep it that way. But so, okay, see if 2 is an upper bound, because 2 is positive now, right? So what that theorem says, if 2 is positive, when you do synthetic division, you're looking for a quotient row that is all positive. Would you agree that these are all positive? Okay? Now, it tells me that is not a 0. 2 is not a 0. It does not divide this thing evenly. Okay? But even though that doesn't happen, and so I know that x minus 2 is not a factor, it does give me insight to this. It tells me you don't need, in your list of P over Qs that you would generate here, if you think about the P over Qs for this polynomial, it's not a large list, okay? It's plus or minus 1, plus or minus 5, right? That's the list for P over Qs here. What this is saying, though, is I now know because 2, which wasn't even one of my P over Qs, but 2 gave a remainder line of all zeros, all positive numbers, okay? Which means then I don't need to check P over Qs that are bigger than 2. I don't need to check 5. Does that make sense? I can cross it out. Now, why does that become beneficial? Because in a lot of P of X's, there are going to be a lot more numbers above 2 that I could cancel out. Might be my entire, or half of my list. It might be 2/3 of my list. Okay? So that's the idea. We're looking for that series of positive numbers here, all positives when this is a positive number, and that will provide us an upper bound. So that means that when you graph this, you will not see a 0. You will not see an x-intercept to the right of 2. Okay? They try -3. Put -3 in here, and we look at this and we go positive, negative, positive, negative, positive. They alternate, right? So because they alternate, that means that, and this was a negative number, that means that's a lower bound. Okay? So, what's that mean to me? That means if I graph this thing, and I find 2 out here, and I find -3 out here. Now, this was a 4th degree polynomial. If this thing crosses the x-axis, okay, it's going to do it between -3 and 2. That's what this lower and upper bound theorem are telling me. Does that make sense? Okay. So if I'm in a problem that had P over Q's that were to that side of 2 and to that side of -3, I could just cross those off in my list right away, and I wouldn't have to check them. I know they're not going to work. Does that make sense? Okay. So I think you're going to find out, guys, that there's some questions and, the tests that I give you, the quizzes that I'm going to give you, which we haven't had one in a while. Those things are going to ask you questions that target the upper bound theorem, lower bound theorem, his name's Rene Descartes. And I keep saying his first name first, but Descartes' rule of signs. I want to ask you individual questions about those to see if we understand what those theorems are saying, what they're providing for us. Generally, though, on like a test, okay, like let's say the final, they're going to give you a P of X and say, factor it. Okay? Do I use this stuff? Is it beneficial to use this? Maybe. Is it beneficial to use the thing in front of me that has all those buttons on it and does things a lot easier? Probably. Okay? So we're going to get into using our technology, okay? But I'm still going to ask you to understand what these theorems are saying. Okay? So let's do this. Let's say that I give you, and this might be a question that I ask, P of X. I might ask a qualitative question about this in a moment. P of X equals 1/2 x to the 5th minus 2/3 x to the 4th plus, let's go, 1/5 x to the 3rd plus 2x squared plus x minus 6. Does the rational root theorem, which remember is our P over Q stuff, work with this P of X? Maybe you can answer that thinking, well, why would he even ask that question? Because normally, if it worked, we would just start doing it, right? So what's the answer to that? Does it work with P of X, just based off that logic? It does not. Okay? The rational root theorem does not work here. Does anybody know why? Here's my question. What are the factors of 1/2? Right? Does that make sense? You know the factors of 6, the two numbers that multiply together make 6, but what are two numbers that multiply together in 1/2? What are those? Okay, when we talk about factors, by definition, when we're doing this, when we're talking about the things that divide evenly into these values, we're talking about integers. Okay? So in order for the rational root theorem, for me to find out what P over Q's are, I need to have integers as my coefficients. That's why at the beginning, when we first introduced the rational root theorem, the rational root theorem has integer coefficients. For any p of x that has integer coefficients. We need to have that, okay? Well, then you might be, well, if that's the case, then I cannot use p over q. And you think, well, what do I do then? Must not be able to, maybe I go back to algebra 1. When I couldn't factor something, we just wrote prime on it, right? We went on the next one. Can't do it, okay? Well, we can do this, okay? Here's the idea. Let's say that I've got, and I'm going to make one here that, let's see, try to think here. See if this will do what I want to. Okay, so I just got this random polynomial here. Okay, it's fourth degree. We see that we do have 4 zeros here, right? Okay, but look at these coefficients. Okay, now this one's a little bit nicer than the one that I gave you prior. But I can't use p over q with this, because I don't know what the factors of 4/3 are. I don't know what that means. But let's do this. Let's take f of x. What can I multiply f of x by to get rid of all those denominators of 3? Can I multiply the whole thing by 3? And it gives me that. Does that make sense? Okay, now, if I multiply the whole thing by 3, I wish GeoGebra would actually... so that 3 is just going to give me 4x to the 4th minus 49x to the 3rd plus 191x squared minus 266x plus 40, right? That's what that red one is. Does that red one have the same exact zeros that the green one had? They cross the same spots, right? Okay. So the idea then is if my goal is to find these zeros, and if I've got this p of x here, and I want to find the zeros, then every multiple of that is going to have the same zeros. I multiply that by 2, and that p of x, 2 p of x, is going to have the same zeros that 1 p of x has. 20 p of x is going to have the same zeros that 1 p of x and 2 p of x have. Does that make sense, everybody? So in that p of x, what would be the best thing to multiply by? 30. It's the LCD, right? Okay. So if I rewrite, I'm going to write this as 30 p of x's would equal, now this would be 30x to the 5th, right? I'm sorry, 15x to the 5th. Be able to do multiplication. 15x to the 5th, okay? Minus, then multiply this by 30, 20x to the 4th. Multiply this by 30, so it gives me a positive 6x cubed. Multiply this by 30, it gives me 60x squared. Plus then 30x minus 180, right? Let's kind of talk about some things here. Let's talk about Descartes' rule of signs. Okay? If I want to know positive zeros, positive zeros is the number of sign changes, right? Is that a sign change? Is that a sign change? Is that a sign change? So I could have 3 positive zeros or that less by an even whole number. So 1. Okay? So let's talk about the negative zeros. Now the negative zeros, I need to go in here and plug in a negative x, right? So p of negative x. And I could do that in either that polynomial or this one that's 30 times bigger. It doesn't matter. But that would give me negative 15 x to the fifth. This would be negative 20x to the fourth still. Okay. This will be negative 6x cubed. This will be positive 60x squared. This will be negative 30x, and then minus 180. And then sign changes there. No. Yep, sign change there. Sign change there, right? So we're going to have 2 or 0. Negative 0. Does that make sense? Okay, so that's the sign change. Okay, that's Descartes' rule of sign. Okay, let's now talk about what our P over Q's are. Okay, so if I'm looking at my P over Q's for this thing right here, let's see. So remember, the P over Q's, or the zeros, the potential zeros for P of X, are going to be the same zeros for 30 P of X. So when I look at P, okay, 180, I think about the factors of 180. They're plus or minus. 1 divides it, 2 divides it, 3 divides it, 4 divides it, 5 divides it, 6 divides it, 7 doesn't, 8 doesn't, 9 divides it, 10 divides it, 11 doesn't, 12 does, 12 divided it 15 times, 10 divided it 18 times, 9 divided it 20 times, 6 divided it is at 30 times. I'm missing one. Which one? 12 and 15, 10 and 18, 9 and 20. Oh, okay, never mind. 5 and 36, that's the one I was thinking about. I think I missed 36. 4 and 45. 3 and 60, 2 and 90, 1 and 180, right? Those are my P's. Here are my Q's. Plus or minus 1, 3, and 5, right? Now, in the whole grand scheme of things, 180 is a small number, or what it could be. Does that make sense? But that gives you 18, if I counted those, I mean, there's 18 factors there. Q has 3 factors, right? What's 18 times 3? 54, right? 54 P over Q's. But they're plus or minus, so that's 108 P over Q's. Would you want to do synthetic division with all those 108 P over Q's? No. Okay? Now, I've done Excel here to make things a little bit easier for us. I don't want to have to write down what all those P over Q's are. So, just kind of use Excel to help me do it a little bit more efficiently. Those would be all our P over Q's, okay? I don't want to have to go check all those. Does that make sense? And those are just the 54 positive versions. There would be 54 negative versions, okay? I don't want to have to go through and check every one of those. So here's the idea. Maybe I start somewhere in my list. I don't know where to start in my list. Maybe I start at 3. Let's try synthetic division with 3 here. If I go 15, negative 20, 6, 60, 30, negative 180, and I put 3 in my box. Bring my 15 down. Does that give me 45 here? Brings down 25, right? 75, 81, 243, gives me 303. 909, so 939, and then what? So 7, carry the 2. Let's do the calculator. 939 times 3, 2817. Okay, minus 180 from that, 2637. 3 is not a 0, right? So 3 can be cut out of my list. But what are all, it's a positive number here. What are all the signs here? Positive. So that tells me that 3 is an upper bound, right? So now I go back to my list, and I go, well, all those don't work. That make sense? That one doesn't work. Those 2 don't work. doesn't work. 3, I know, doesn't work. Okay. That one doesn't work. Okay, I've got this. The way I set this up, that's kind of weird here. That's putting these, but basically these now are the values that I would check. Does that make sense to everybody? I've now, because it didn't give me a 0, but I'm able to use that upper and lower bound theorem to dwindle my list quite a bit. Okay. We could maybe try a negative number. Maybe I try -1 and see what happens. Maybe they alternate and say, okay, well, now I don't need to try anything less than -1. So that cuts my negative list down substantially. Okay? So that's the benefit of the upper and lower bound theorem. Okay? Now, real quick, what if I want to use my calculator? We should be able to use our calculator. If I graph, if I go through this P over Q, my P values are going to be plus or minus 1 and 3, right? My Q values are 1 and 3. If I divide those, I get 1, 1/3, and 3. Those are my P over Qs. If I try 1, 1/3, and 3 in synthetic division with that polynomial, none of them give me a 0. Not a single one of them give me a 0. Okay? So that means, and we can kind of verify this real quick here, 3x to the 4th plus 4x cubed minus 7x squared minus 2x minus 3. Okay, so my P over Qs were 1, 1/3, and 3. Are those numbers that? No, none of those. Okay? But this still has zeros, right? The zeros for this those would be the zeros. Okay, my hopes are you can see that there. You probably generate that from the quadratic formula. Okay, but those would be the zeros of this blue polynomial. Are they rational? No. Okay, so the P over Q only gives me rational zeros. You can have irrational zeros. Okay, and we'll talk about maybe how we can deal with figuring out irrational zeros. Okay, it's not as easy as P over Q. P over Q is still tedious. So if I say it's not as easy as P over Q, you can kind of maybe imagine how difficult that is. And a lot of techniques that we use to find irrational zeros is an approximation technique where basically it's kind of an upper and lower bound idea, but then you start kind of reducing those upper and lower bounds. You reduce the upper bound a little bit, or increase the lower bound until they meet in the middle, and when they meet in the middle, that would give you the 0. We're not going to do that stuff, but yes.
Well, one of those beats, the one we just in class, be like that on the test, but like not as many possible.
Yes.
Okay.
Yes. Yeah. I'll keep the numbers where like maybe there's like at most like 10 P over Qs.